The transhipment problem is a linear optimization problem. And the simplex algorithm that we have seen requires the problem to be written in standard form. This is what we will do in this video. So this is the transshipment problem. It's a linear optimization problem that minimizes the total cost of the flow, subject to the flow conservation constraint. The divergence of each node must be equal to the supply-demand data, and to the capacity constraints, the flow must be between the lower bound and the upper bound. The first thing that we have to do in order to write the problem in standard form is to set the lower bounds to 0. This can be done easily by a change of variable. So we define the new variables x prime ij to be equal to xij minus lij, where L is the lower bound. Now the objective function is the sum of the new variables times the cost minus the sum of the lower bounds times the cost. But this last term here is a constant. It does not involve any decision variable. So it means that it can be omitted from the objective function without any problem. It doesn't change the solution of the problem. So we are left with the sum of the total cost for the new variables x prime. Now we write the flow conservation constraints. We write these constraints in such a way that the decision variables x prime are on the left-hand side, and everything which is constant is written at the right-hand side. So because of the shift, now the supply and demand becomes SI, the supply and demand of the problem, plus the sum of the lower bound of the incoming arc minus the sum of the lower bound of the outgoing arc. And actually we can consider this quantity here as a shifted supply demand information that we denote by SI prime. So interestingly, the form of these constraints is exactly the same as before. We have the divergence here for the new variable must be equal to a quantity which can be calculated. And then we have the capacity constraints. The new variables must be between 0 and u minus L. So this is how we define them, and to set the lower bounds to 0. And actually this difference between u and L, we can call it u prime. It is a quantity that becomes an upper bound for the new variable. The first set of constraints must be true for each node, and the second set of constraints must be true for each arc in the network. So we have seen that after this transformation, the problem is written is exactly the same way as before. We have just shifted the variables, but the form of the problem is the same. The cost function, flow conservation constraints, and capacity constraints, where the lower bound now is equal to 0. The second thing we have to do in order to get a problem in standard form is to transform the inequality constraints into equality constraints using slack variables. Here, the only inequality constraints that we have is that the flow must be less or equal to its upper bound. So we will have to include a new slack variable per arc in the network. For each arc, so we have that x prime ij must be less or equal to uij. So we introduce the slack variable yij for each arc ij, and we have the following constraint. It's an equality constraint, x prime ij plus yij is equal to uij, to the upper bound, and both variables must be non-negative. Now the interesting thing is that we can actually interpret these constraints, which are now equality constraints, as flow conservation constraints. This is less easy to see, so let's use an example to illustrate the concept. Consider this simple example. I have one arc, ij, with a cost, a flow, which must be between 0 and u. The node I is associated with a demand Si prime, and the node j is associated with a demand Sj prime. So this is the original formulation after the shift of the variables to get the lower bound to 0. The idea is to include new variables, the slack variables, associated with an arc. And in the transshipment problem, a variable is associated with an arc in the network. So the fact that we add a new variable somehow can be interpreted in adding new arcs in the network. This is what we have represented in the second part of the picture. So here we have added a node, an artificial node here. Here we have the original arc associated with the cost Cij. But now we have added a new arc from the artificial node to node I, and this arc here is associated with the slack variable, and therefore its cost is 0. Okay, the slack variable does not play any role in the objective function. And now the idea is the following. Let's inject in the network the quantity Uij at the artificial node. And then this Uij will split between the two arcs, the original arc that will carry the flow x prime ij, and the slack arc that will carry the flow yij. By construction, the quantity of flow that will be carried by this arc here will never exceed Uij, because this is the flow which is injected here. Meaning that on this arc, we don't need anymore to impose an upper bound. We can put it to plus infinity. And whatever is not carried by this arc will be carried by the slack variable. Good. So this is very useful because we don't need upper bounds anymore, either for the original arc or for the slack arc. But we have transformed our problem. We have put too many flows in the network. So all the flows that have been added here must be removed somewhere. And actually what we will do is to remove it here, so that globally the total demand will be exactly the same. In summary, adding a slack variable to an arc with upper bound Uij consists in adding a new node and a new arc, which is the slack arc. We inject at the new node the value of the upper bound Uij, and we associate the new arc with a cost of 0. The final thing we have to do is to update the values of the demands so that the extra flow which has been injected is immediately removed after the slack arc. And in that case, we don't need to impose any more upper bounds on the flows. Let's take now a numerical example to illustrate the two steps of the transformation. So we have one arc, ij, 3 units of flows are injected at I, carried by the arc, and consumed at j. This is a very simple example. The arc is associated with capacity constraints, a lower bound -5 and an upper bound which is +5, and a cost Cij. Now we transform it by first shifting the variables to set the lower bounds to 0. So we need to shift them by 5. Therefore, the quantity of flow now from the new set of variables moved from 3 to 8. The bounds are shifted also from -5 to 5 to 0 to 10. And we have, of course, to adjust the demands. So here we have now 8, and here we have -8. This new formulation can be interpreted as 8 units of flows injected at I, carried by the arc, and consumed at j, with a capacity constraint which is 0, 10. So it can be interpreted as a transshipment problem as well. Now we need to get rid of the upper bound, which is 10. We include the artificial node here. The supply of this node is 10, the value of the upper bound. So we inject 10 units of flow here. And in our example, the true arc, the original arc, is carrying 8 units of flow. So among these 10, 8 units will move along this arc to reach j here. So that the demand at j is satisfied. So j will receive 8 units of flows as requested. Now the slack, the excess of flows, that is 2 units of flows, will follow the slack arc here, 2 units of flow. But it means that the global flow which must reach node I is not the same anymore. We had originally 8 units of flows, but now we need to put -10 because we put 10 flows too much on the network. 8 minus 10 is equal to -2, which becomes the new demand for this node. It means that to transform a transshipment problem in standard form is equivalent to modify the network in the way that we have described here and write the transshipment problem for the modified network where all the arcs have a lower bound which is 0, an upper bound which is plus infinity, and then we have flow conservation constraints both at the original nodes and the artificial nodes that we have included. This is great because we can now think as a transshipment problem directly written in standard form, and we can directly apply the algorithm. It is convenient to write it using the matrix notation. So we have the minimization of C transpose X, which is the cost vector, subject to AX equals S, where A is a matrix with M row, which is the number of nodes, and N columns, which is the number of arcs in the network. And S is the vector of supply-demand data, which is of length M, which is the number of nodes. And of course, C is a vector with the number of arc Rn. The matrix A here has a very specific structure. This is called the incidence matrix. Because of the form of the constraints, so each row corresponds to one of these constraints, and this represents the flow conservation constraint. So we have a node I. For each node I, the first term is the sum of the flows going out of I, and the second term is the sum of flows entering I. If we look at this matrix not row-wise anymore, but column-wise, suppose that we have here a node J, we have the arc ij here. Well, the arc ij will appear only in two constraints. The constraints of node I, where it will appear in the first term, so with a coefficient which is 1. And the second constraint where it will appear is in the constraints for node J. And because it's an entering arc for node J, it will appear in the second part of the constraint with a coefficient -1. So it means that in each column of this matrix, the column corresponding to I and J, there will be a 1 at row I and a -1 at row J, and everything else will be 0. This is a very specific format due to the nature of this flow conservation constraint. Let's take an example of the incidence matrix. So here I have a network with 6 nodes, and I will write the 5 first columns of this incidence matrix. So here, each row of the matrix A represents a node, and each column represents an arc. And it has more than 5, but I will just write the 5 first. If you take the first arc, which goes from 1 to 5, it means that we will have to put a 1 at row 1 and a -1 at row 5, and everything else is equal to 0. Arc 2 goes from 1 to 4, so I put a 1 in 1 and a -1 in 4, and 0, 0, 0, 0. Arc 3, 5 to 3, 5 is 1, 3 is -1, and everything else is 0. Arc 4 goes from 2 to 3, so 2 is 1, 3 is -1, and then I have 0, 0, 0, 0. And the last example, 6 to 2, so there is a 1 in 6, a -1 at 2, and then 0 everywhere else. This matrix is called the incidence matrix, and its special structure that we have seen here will actually provide us with interesting properties. We have seen that the standard form can be interpreted as a transhipment problem on a modified network. We have also seen that the matrix that characterizes the flow conservation constraints has a special structure. Each column, corresponding to arc ij, contains only 2 non-zero entries. There is a 1 for row I and a -1 for row j. This matrix is called the incidence matrix.